Now live stream. Let's capture it.
All right.
You have to start over. Okay, yeah. Go for it.
All right. Did some past research in NFC, mobile wallets, and some Bluetooth stuff. Today we're going to be focusing on the Android open source project and OEMs, and then what the OEMs add on top of the Android open source project, and then what the consequences are. So we've seen a lot of rooting exploits and application issues and privacy issues come out of the pre-installed applications, modifications to the Android open source project. So this is really focusing on that today. We've seen a lot of OEM-specific vulnerabilities in chipsets, backdoors in devices, and in preloaded applications. So it says 4.0. It's really an overview of rooting post 4.0. So there's a huge difference between Android 2.x, 3.x, and 4.x. And 4.0 just makes a better joke because it's ice cream sandwich. So the Android open source project is what we call Android. It's comprised of a kernel, a hardware abstraction layer, some system services. So OEMs can port this to their device, but then it's up to them to interact with the hardware abstraction layer and provide the hardware abstraction layer code, drivers. The Android open source project can really only be built, like cloned, built, and pushed for the Nexus devices, Nexus 4, 7, 10, and some of the Galaxy Nexus devices. So if you try to build it for like your Samsung Galaxy S3, you're going to be missing a ton of stuff. A lot of drivers and hardware code. We're not going to be focusing on the Android open source project, just to be really clear. We're going to be focusing on the OEM components. So I'll do a quick overview of device components. How many people have heard of bootloader recovery and know about file system permissions on Android? Like half? Okay, cool. The main job of the bootloader is to ensure that only signed code can be booted. We're going to look at developer unlock versus exploit unlock of the bootloader. And this is where we see a lot of the 4.0 roots coming from. We'll look at the recovery partition. The main job or the main reason you want control of the recovery partition is because it allows you to mount the file system as read-write and as the root user, write to it as the root user. So that's like Clockwork Mod, TeamWin Recovery Project. Those are written to the recovery partition. We'll look at file system and permissions. So /system is where a lot of binaries are. It's mounted as read-only. It's where all the pre-installed applications are on an Android device, /system/app. /data is where all the user data and user apps are stored. Data local prop will come into play later. That's some of the Android device-specific settings. And we'll look at symlink attacks that attack the data local prop, data and data local temp directories. So to start off with bootloader unlocking. If you unlock your bootloader, it means you can boot unsigned code. HTC was calling this S on, S off. That's like a little bit lower layer. That's a flag on their radio. On a Nexus device, you can tell the bootloader is unlocked. When you boot it up, it'll have a little lock or an unlock sign. Qualcomm has an indication also on their bootloader. There's two very different scenarios. There's the developer unlock, where you're wiping the /data partition. And then there's the exploit scenario, where you're not wiping /data, so all the user data is intact. So on a lost or stolen device, that's pretty bad. So these are two locked bootloaders. You can see on the left is a Motorola, an HTC, and on the right is a Samsung, and they're both locked. You see at the top it says locked and S on, and at the bottom there, Qualcomm Secure Boot Enable. I don't know, maybe you can't read it. It says official. So we'll see what those look like when they get unlocked. Some examples of bootloader exploit unlocking. The first one we saw was unrevoked, so that was for HTC only. That was a pretty cool program, and it affected, like, I think most HTC devices a while ago. More recently, MotoChopper. It's called MotoChopper, but it works across several OEMs, and that's a Dan Rosenberg exploit. And there's Odin and Heimdall, which are Samsung programs. Or Odin is the Samsung program, and Heimdall is the open source implementation. So that allows flashing custom bootloader which doesn't enforce the signature checks. And on some of these, the data partition is not cleared. Whereas a developer unlock is something that you're doing through HTC Dev, or Motorola is now doing the same thing. It uses fastboot and device token. So HTC Dev is HTC sanctioned, and it's the way that HTC allows you to have a developer device. You feed a value to HTC's website, they spit back a token, you put that into your device through fastboot, and it'll prompt you and say, do you want to unlock the bootloader? It's going to wipe all the data, and it's going to possibly void your warranty. So that's like the developer unlock scenario, and that's generally okay. This is what the bootloaders look like unlocked. You can see at the top there, unlocked, and then custom, and it's got a binary counter. Nexus 7, the Nexus devices are really easy to unlock. Fastboot OEM unlock, it's going to prompt you like it says here. And then on the left there, you can tell the bootloader is now unlocked. So your warranty's void and all the data has been cleared, but you've got a bootloader that can write unsigned code, or can boot unsigned code. Relocking it is also simple, doesn't wipe the data. Okay, even though you unlock your bootloader, you still don't have root. What the heck? I just want root. So all it does is allow you to load this unsigned code. So the next step is the step where you get root. That's where you can flash a custom ROM or a kernel or a recovery image. And we mentioned before, the recovery image will let you write to the system partition as root. Clockwork mod, TeamWin recovery project. I mean, there's a million recovery images. I like Clockwork mod because it's easy. The purpose of this is to just write that SU binary pre-boot to flash it onto system. And then when you boot the device, you have access to the SU binary. It also allows for low-level imaging, which is really, really useful, but not an exploit scenario. Okay, finally root. So all root is on an Android device is a binary with a setuid bit set. You don't need the super user APK and all that stuff that surrounds it. You're just trying to get one little binary on there. There's another case, debugging root, where there's no binary involved and applications don't have access here, but from the Android debugging bridge, you can act as the root user. So data local prop comes up again. There's a couple other settings files that you can modify. We'll just look at this one. If it has any of these flags, RO debuggable equals 1 or RO secure is 0, when you reboot the device and ADB onto the device, you're going to be the root user. So if you wanted to hide root, because it's just a binary, it's really easy. It's really, really difficult for an application to do a full root check and reliably determine if the device is rooted. These are some of the really simple things you can do to hide root. You clearly don't need the superuser.apk. Applications will look for system mounted as read-write, but once you've written to it, there's no reason to have it read-write. They'll look for junk in /data local temp, and then they can actually just look for the SU binary in system bin, system xbin, but it can be anywhere on the file system. It doesn't matter. So what I usually do is just rename it to blah. So I have system xbin blah, and I haven't found an app yet that checks for blah on the file system. But you can see there, still it's owned by root and it's got the SUID bit set. So the ways that you can tell it could be a root shell. Okay. So we'll divide the rooting exploits that we see up into 3 different categories. Drive-by roots are obviously the worst kind. Malware could potentially exploit these, and they could have malicious intent. Then there's the user-initiated roots, which are kind of in the middle. These are a lot of like your XDA forum roots, where you need physical access to the device. You might need to be rebooting it or interacting with the device somehow. And then the last one's data wiping roots. So this is where you're purposefully switching the device to developer mode, like we saw, and it's wiping all the data. So it's not a big deal for a lost or stolen device. Carriers obviously don't like rooted devices on their network, so they may try to prevent these, but it's not an issue for data security. So a drive-by root is something that an attacker can execute on a locked device. So if you found this device somewhere and you knew, it was locked, and you could execute an attack somehow and gain access to the data, that's a drive-by root. Or something that malware could execute just as an application on the device. Of course, if you have ADB enabled on your device, it opens up a lot more avenues for attack and a lot more exploits that are possible. So we'll assume no ADB. User-initiated roots can't be initiated by malware. It's something the user has to, like I said, be interacting with. Some are complex. They can brick devices, and then some are really simple. So the LG one is, I think, one of my favorite ones, and we'll walk through that later on. And then data wiping roots we've covered. No risk of bricking it. You're just enabling developer mode. Okay, so now to the meat of what we've seen in Android 4.0 Plus. So the reason I picked 4.0, aside from it making a good joke, is that 4.0 brought a lot of new security features. So there's on-device encryption, fully implemented ASLR, DEP, and it makes it much harder to write local exploits, local privilege escalation exploits for the Android open source project. So we've been seeing the rooting community kind of moving to the fringe components, which is the OEM components and applications. We used to see a ton of just simple privilege escalation exploits on 2.3, 2. Whatever. Post 4.0, Mark and I were talking about this. I think there's one-ish exploit. So the ADB recovery arbitrary file write was definitely like a universal Android open source project. You made a mistake, error. And it was a race condition. It would allow arbitrary file writes, which you could leverage into root. The master key vulnerability affected 4.0, and it was discovered when 4.x was the latest version, but I think it went way back to like the beginning of Android. So that one is the ish part. It doesn't really count. So how are devices getting rooted? Devices will come out and 2 days later they're rooted, and everyone on XDA can root their device and install CyanogenMod. A lot of it is hardware-specific privilege escalation. So Exynos was a Samsung chipset, and this was Exynos abuse was an exploit specific to this chipset. Moto Chopper, while it's pretty much as close as we've seen to a universal Android root in 4.x, it's Qualcomm chipset specific. And then we've seen some OEM-specific backdoors, which is just where the OEM either leaves it by accident or puts it into their particular build of Android. So the ZTE hard-coded password made the news. That was like a really big deal. People were mad about that one. And it was just a set UID binary on the device, and if you gave it some random string, it would give you a root shell. The LG one is really cool. So we'll walk through that one. It's just nice and simple and fun. Then there's OEM file system permissions. So if the demo gods don't hate me, I'll go through rooting this device. So real briefly, Exynos, it was an ARM-based system on a chip manufactured by Samsung. And it was Exynos 4412 and 4210 processors. The way they mapped memory was to just have /dev/Exynos mem, and you can see on the bottom there, that's how it was before the patch. And then the top one, I obviously should have reversed them, is how it was after. So it's read-write for anyone, right? Other, read-write. And what that device did was just map into physical memory. So you could pretty easily search through physical memory, figure out whatever bit you need to flip to be root, and do it. So Aleph Zain wrote Exynos abuse, which is just an APK, gets loaded on your device, and it'll provide the patch. Obviously, the real patch is a kernel patch, but because you have read-write and you can root the device, you can lock down, so it's only readable by the system user. Moto Chopper is one of the most complex and intricate roots, I think, that we've seen recently. Dan Rosenberg found it and packaged it into this nice little package from Azimuth. So it's an ARM trust zone exploit that unlocks the bootloader of a device, and it's called Moto Chopper, I assume because he found it on a Motorola device, but it affects almost everything. Like, I think I rooted this one, and like this one using Moto Chopper. So Samsung and like Huawei. I mean, it affected any device using this Qualcomm MSM 8960 chipset. And it was a really clean exploit. So here's the LG backdoor, and maybe just from the strings here, you guys see where this is going. It's not a remote backdoor, so LG doesn't have access to your device, but it could allow a user to obtain a root ADB shell. It's not putting a binary on your device like we talked about. It's just running ADBD, the daemon that you connect to with Android Debugging Bridge. It makes that run as root. So credit goes to this guy whose name I don't think I can say safely. So I rooted the device and just pulled off ADBD and threw it into IDA, and you don't even need to understand assembly to figure out what's going on here. You see it's opening this file, /SD card /gsecurity read, and then skip all the complicated stuff and just go to the bottom and it says, check LG official, enable root. So all you need to do is follow the directions and you get root. So on this device, shell, you can search for the file, it's not there. Just touch it. It doesn't have to have anything fancy in it. Restart USB debugging, shell, and you get root. So applications can't use this, right? Because it's only ADBD running as root. It's not like there's an SU binary on your device that an application can exec into. So it's kind of an interesting, excuse me, I need my ice. It's kind of an interesting backdoor. Obviously, if an attacker steals your device and is able to put that G-security card file on your SD card while the SD card's out of the phone, then put it back in, and ADB is running, it's going to be root. So if they had stored this file somewhere other than the SD card, then it would be like a pretty nifty backdoor to just allow users unlimited access to their phones. So it's hidden, but not so bad. There's a new LG root LG Pwn, or it's maybe a couple months old now. And I'll harp on this like general idea more later, but the idea is don't reinvent the wheel. So there's an LG backup app, and JCase exploited a race condition in the LG backup app. But there's also an Android backup app, so you don't need your own backup app. So this was a really bad one. It could be a drive-by root, and it affects 40 plus LG devices. Okay, I'll try to do this one, and if it fails, I factory reset this morning. There's nothing special about it. I just want to boot into FTM mode, which is factory maintenance or something. So I hold volume down and power, and it should boot up into FTM mode. And by the way, this is not like a 0-day root. Somebody published this already. Okay, so it's in FTM mode, like it says in the screenshot. And then oops.
Command plus.
Command plus. Okay, cool. Okay. Okay, so normally you don't have read permission on data local. So that is the big difference. Oops. I still can't use a Mac there. So that's how it should work, permission denied, but that's how it works in FTM mode. So that allows you to symlink that directory. Whoop, come back, okay. Let's see. So we'll just get out of here, and then we'll just back up data local temp, and then symlink data to data local temp, and then reboot it. So does anybody know what's going to happen now? Data local temp is the directory that has read, write, execute for everybody. So since we've symlinked it, when the device reboots /data, we'll get the permissions of data local temp. So we should be able to write into slash data. And what's in slash data that we care about is the local.prop file, right? So if we can create that file and write one of those directives into data local prop, we should have root on the device. So it's still rebooting because it's an old device. Okay. So, oops. What happened? Come back. Okay. So now we can list out data, right? And we couldn't do that before. So now maybe we can try to get out of there and just do that. So we just created the data local prop file with that directive ro kernel qemu, and then we'll reboot it. Okay. So we'll wait for it to reboot, but when it comes back, it should be root. So there's two issues with this, right? The first one is that the initialization script isn't checking if slash data is symlinked to anything, or I'm sorry, if data local temp is symlinked to anything before it sets the permissions. And the second issue is FTM mode. That should be on like a debug device or an engineering device, but not a production device. So it's still booting up. Let's see. Whoop. Okay, so we got root on that device. That one worked. All right. Back. Okay. All right. That was the backup slides. Okay. So we've seen a bunch of OEM exploits based on OEM components, right? Default applications are another really interesting attack surface on these newer Android devices. So they will turn your slick little Android man into Jabba the Hutt because he will have so many applications in his belly that he can't function. So default applications, well, actually all applications have unprotected or protected Android endpoints. So this is the way that applications are supposed to communicate with one another in the Android operating system. They're supposed to use these inter-process communication endpoints: content providers, activities, services, and receivers. They can also share UIDs, and then we'll cover permission leakage and why that's such an issue with all these apps on the device. So activities, services, and receivers are the main communication methods. They can be activated via Android intent messages. Intents can be sent via ADB from an app. They're intended to be app to app, but they can be sent via the activity manager just for debugging. Intent filters are declared in Android manifest.xml. How many people are familiar with this type of thing? Okay. So you can see on the top in the Android manifest, just flashlight test, like the most benign one possible. And then on the bottom there, just activating that through Activity Manager. You just do it from the shell, so it's really easy to script. And that's intended. Content providers are another story. So we'll go through each of the endpoints. The content providers are an inter-application database connection. They can also support files, which is pretty important later on. You access via content : / Drozer has a great interface for doing dynamic testing and querying content providers on a device. They specify an authority for access. So when you're looking through the manifest and you see authority, it goes content : / authority. Activities are what make up the user interface. It's an interactive screen. They can contain an intent filter, so you can launch an activity directly. Like maybe if you wanted to compose an email message from another application, right? It'll just launch that directly through an intent message. Services are designed to run separate from the application. Another application can either just start up the service and it goes, or it can bind to it and communicate through real low-level binder. it avoids blocking the main thread, and a service can contain an intent filter. So you can also launch a service via an intent filter. Receivers, broadcast receivers, will receive an intent that is broadcast to all applications registered with the operating system. So an application gets installed, it says, here's my broadcast receiver, here's the intent filter. I want to register to receive these types of intents. When an intent is broadcast through the system, the operating system says, oh, I know that you wanted to receive this, so here, and it'll send it out to everybody instead of an explicit intent message. So there are some general protections to protect these endpoints. There's Android manifest permissions. So you can create custom permissions in Android. When you create them, they should be in your namespace, and ideally they're protected with a signature type permission. So there's signature and signature or system. Signature means that only applications which share a signer with the creator of the permission will be granted that permission. And signature or system just expands it also to /system/app, which is all the pre-installed applications. You can set components to be not exported. So activity, service, receiver, if they have an intent filter. So this is complicated. They're exported by default pre 4.2, but post 4.2, they're not exported. So they're false by default unless they have an intent filter. And then it's assumed that that's meant to be accessed by something else. So you should explicitly set this always to Android export equals false unless you intend for another application to call it. False just means it can only be interacted with by the same PID, so within your application. Content providers have a little bit separate permissions. So there's read permission and write permission on the authority. So you can query the database with a read permission. You can insert, modify the database with a write permission. And keep in mind the content providers also can support files. You can set exported equals false. So that's the default in post 4.2. So content providers can't have an intent filter because they can't work that way. So exported is always false. Post 4.2. Pre 4.2, it was always true. They were always exported. The kind of gotcha is that the min SDK version has to be set to 17, which is 4.2. So if it's not set to 17, even if you're running on 4.2, you can be running on 4.3, it will still export the content provider. Activities can have permissions. They can have exported equals false. Same with services. Receivers are a little bit tricky. Any app can register a broadcast receiver for anything, but the sender of the broadcast specifies the permission that the receiver needs to access that broadcast. So it's a little bit backwards. And exported can be set to false on these also. I guess if you'd want to do broadcast within your app, then they won't go outside the app. Okay, so permission leakage, we mentioned before, is a major problem with preloaded apps. There's two layers of preloaded applications on every device that gets to you, except the standard Nexus devices. You've got the OEM apps, right? LG, Samsung, Huawei, whoever. And then you have the MNOs applications. You have AT&T, Verizon, T-Mobile, Sprint, whoever. So you've got two layers, and eventually you've got Jabba the Hutt with all the apps. And they're installed with default permissions that aren't explicitly accepted by the user because they're already on the device when you get the device. And there's no guarantee they're locked down. They've got the permissions, right? But you don't know what they're doing with them. For example, and this is something that we've seen in the real world a lot. You have a weather application that's pre-installed on the device, and it has GPS and Wi-Fi permissions maybe. The attack surface on it is a content provider with no permissions and activity with no permissions. So the activity in and of itself is not a problem. We don't really mind that. But all it does is open up and it'll get your GPS location and it'll update the weather. But maybe the content provider, which is unprotected, will provide your GPS location and the current weather. So an attacker or a malicious application could call the activity, update the GPS, and then query the content provider, and then you have the device's location, which is protected by a separate explicit Android permission. So you can see how permission leakage works. An application already on the device abuses a permission that it has and presents it in a kind of open fashion, and any application on the device can access it. Android SMS spoofer was a really cool example of this. Thomas Cannon released it October last year, and this was actually an issue with the Android open source project. COM Android MMS exported a receiver service that had no permission restrictions, and that was used when you received an SMS to alert the user. So for smishing attacks, this would have been particularly useful. Any application could send an SMS. It wasn't really sending an SMS, but to the user it appeared that a new SMS came in, and it could be from any phone number and it could contain any text. Okay, so because all that stuff is so complicated, I made a tool. And the tool is a manifest analyzer, and we affectionately call it Analfest. A coworker came up with it, and I can't get it out of my head. So it parses the Android manifest.xml file, and it parses it into objects just like you would for like standard XML parsing. But then those objects can inherit from each other, right? Because if you look at an Android manifest file, it maybe goes like 5 elements deep. So you want to have permissions inheriting from all of the parent objects. And what it'll do is just kind of spit out unprotected components. And it does a couple extra things. It'll spit out like shared UIDs and stuff that we'll get more later, and custom permissions. So let me start this demo because it takes a little while. Some of the stuff I added in. So if ADB and APK tool are in your path, it'll just work. But if they're not, it'll probably bomb out. So let's see. There we go. So here's the help menu. Here's all the things that it can do. So the options that we want are get, and then filter for ulong. So this device is a cool pad, and it's made by Ulong, and it avoids having any US carriers as part of my talk. A friend just got it from China, and it's on China Mobile, and so far it's been a really fun device. So we'll just grab all the Ulong apps off here. Oh, good. Oh. I knew I wouldn't get that lucky. Oh no. Okay, if this doesn't work in 2 seconds, I'll just move on. Oh no, I've done it a bunch of times. I actually did it this morning, but... Okay, here we go. Connect to Mac. Okay, turn on USB debugging. Okay. Oh no. Well, it sees it. I really wish you would connect. Oh man. Okay, well let's try this one because it's just a quick demo. Okay, well that's fine. It won't find any Ulong devices though, or apps. So here, this is a Samsung device, so we'll just pull off, I don't know, pick something. Pick off mail, anything that says mail in it. So it'll just hook up to the device, look through the packages list. Oh, sorry. Grab all the packages and then decompile them. So moving on with the Ulong device. Oops, where'd it go? Okay, so the Ulong device was cool just because it had such an obvious error where they had a content provider that was unprotected, and the content provider contains all of the notes that you write. So It takes about 2 seconds to find the bug with Analfest. You just run it, you pull off the app, you see that it has, I'm sorry, it's really hard to see. You have content, com, ulong, Android, memo, provider, note, and you can select in there and it says my secret note. So it's just a good example of an unprotected content provider that probably wasn't meant to be exported that has all of your notes in it. So here's another content provider. This is what it looks like in the manifest and what Analfest spits out. And the point of Analfest is to just give you some idea of the attack surface of a device. It's not going to reverse engineer the app for you or tell you how to exploit it. It'll just tell you where a good point to press might be. So here are some unprotected services from an OEM app. This is from a Huawei app. And this is just a copy file service. So ostensibly it takes in a file to copy and puts out like the location you'd like it copied to. And then an activity. Activities are really interesting because you're looking for hidden menus or kind of malicious inputs that you can include. It'll take in extra data from the intent message. So activity manager, you can use extra string or extra int or anything. And if you reverse engineer the application, it'll tell you what it's doing with that and what exactly it's looking for. So JCase found a really cool bug with a debug activity where it would ping, and you could do command injection into the ping prompt, and it was running any command as the system user. So that was a debug menu that you don't need to have on the device because you can just launch it directly through an activity. Excuse me. You can run commands as the system user. So this one takes in, you can see here, if you just do dextrajar, you can see get intent and then get string extra. The extra is path that it's looking for, and it takes in a file path. And when you run it, it'll open up the activity pointing to that path. So if you wanted to open up your camera, you would do that. Okay, Quark's Lab had a great talk where they picked on one OEM in particular. And I think the OEM has patched almost all of the bugs that they found, but this one was definitely my favorite. It was a broadcast receiver, excuse me. And it was a lot more detailed, but if you traced it through the app, there was a function called do shell command, string param string, and the user controls param string. So they were able to escape out of that and run a command as the user of that app. So, oh wait, we'll save Picard for a second. So here, I happen to have a vulnerable device plugged in. That's what I was going to use it for. Oh, there we go. Oh man, it only found one file. Okay. Well, we'll try the ulong device later if we have time. Okay, so this has been patched since, but this is an older device that I keep on airplane mode and don't let it update. So this was the exploit. It's just activity manager, AM, which I mentioned before, broadcast, and then the extra string is file name, and then, oops. There we go. And you just escape out dev null, and then run system bin ID and put it in a file in the SD card. And the phone lights up and says, get copy log success done, all this stuff. And then you can just cat. And there you have the output from your command. So that was, again, through an OEM, just debug prompt or application. Okay. Okay, now Picard gets to say his piece. Don't re-implement functionality that Android already has. So app stores, Wi-Fi hotspots, Wi-Fi connection managers, backup programs. We've seen critical bugs in all of these types of applications, and Android provides it. So there's no reason to re-implement it. Okay. So example App Store issues. App stores are really tricky because you're dealing with signatures. So there's really no clean way other than using the Play Store to validate the signature on an application. So we set our intern on it this summer, and we handed him a device that had an app store that installed packages without verifying the signature and ran over HTTP. So one thing that he was able to do was man in the middle of the connection and then have a cache of apps that he'd already modified, or he could just do it on the fly. User downloads the app comes in, he man in the middles it, decompiles it, injects Smolly, repackages it, because no one cares about the signature, it just goes down to the user's device, and then it would call back to his server. So that was a cool bug and an example of why you don't implement your own app store. We see shared system UID a lot on pre-installed applications. Every Android application has its own UID, and system UIDs are under 1,000. Application UIDs are over 1,000. So Analfest will check UIDs. Actually, let me reboot this. Maybe that'll fix this. Okay. And then the more critical thing that we see is shared application UIDs. So I had said that content providers can support files. If you have several applications on a device that share the same UID, and one of them has a content provider that supports files and is vulnerable to directory traversal, which we see a lot, and actually Drozer has a module built in to check for that, you'll be able to access the files on any other application because they're all sharing a group ID if they say share UID, this UID. And you can read from their sandbox directory. So the Android open source project can implement all the security in the world and be as secure as it possibly can, but until OEMs start testing their apps and keeping security in mind, any device that gets to you, the user, that's not an immediate Google device is going to have all these problems. And the worst part is you're not going to be able to fix them by uninstalling the apps. So as OEMs, don't modify the Android open source project. But that's probably not possible because everybody loves the OEM look and feel on every Android device, right? Patch vulnerabilities and then deploy the patch quickly. Unfortunately, that requires a lot of cooperation between the OEM and the MNO. Bundle as few applications as possible, or maybe even don't put them in /system/app. Put them in data app so the user can uninstall them. And use a locked bootloader. Don't share UID unless it's absolutely necessary. Keep everything sandboxed. It's really nice and seems really neat to have everything sharing a UID, but it really undermines the Android security model. What MNOs can do. So you can vet all the preloaded applications that come from the OEMs, and then you can vet your own applications, and you can push out patches quickly. So when the OEM pushes down a new version of the operating system that might fix some bugs, you can go ahead and push that out. You can mandate the latest software versions on your devices, and then you can, really get on the OEMs to keep their builds up to date. And most importantly, don't reinvent the wheel. So what you can do as a user, first you can install CyanogenMod. Other than that, you just have to hope and pray that your device stays up to date. And a lot of devices kind of fall out of favor in 8 to 12 months anyway, and you stop getting updates. Be really careful when downloading from marketplaces. Only use Google Play. Everything else can't possibly have a reliable method of checking signatures of apps. If it makes you check the unknown sources box, it's not checking signatures anymore. Don't root your device. If you do root it, just hide the binary. Make it blah or your own special blah. If you want to unlock the bootloader, maybe lock it after you're done. And then most importantly, check permissions when you're installing apps. So in the future, we'd like to see maybe a Google-controlled secure boot chain. 5 minutes. All right. Native support for more hardware. which would prevent mistakes from OEMs and these kind of Exynos or MotoChopper exploits that we've seen where someone other than Google is writing the code to interface with Google's operating system. And then ideally, the ability to revoke application permissions. If I have a pre-installed app and it's got 10 different permissions and I don't want it to have all those, just uncheck a box. That would be really simple. Okay, I didn't really get to demo that tool, but there it is. I'll be updating it in the coming weeks if you want to check it out. I'll try it one more time while we do questions. That's my Twitter. I don't tweet very much, but I follow people. Big thanks to Nitin and everybody at IG. That is all. So let me just see if this will... Oh, man. Okay. Okay, any questions? Did you raise your hand?
Yeah, is this at all related to the management project you guys had?
Manatry.
This is the new version of that.
Okay, so this is the successor?
Yeah. Much more successful.
Oh, there.